Hi, good afternoon. It's a pleasure to be here. I'm here to talk to you about Go assembly today, and in particular some tools and techniques that can make it a little easier and safer to work with. So what is assembly language? Go provides the ability to write functions in assembly. And assembly is a general term for low-level languages that allow for programming at the instruction-by-instruction level for a particular architecture. When I think about all of the layers in modern software and hardware, I can't help but think of the phrase, it's turtles all the way down. So you've got this massive stack of layers, and if you're in assembly, you're working, you're at one of the bottom of these turtles. Let's just start with, just because you can write functions in assembly, should you? Probably no. Channel your inner Rob Pike and remember some Go proverbs that he did not say, but he might have. First off, assembly isn't Go. Assembly is not portable at all. If you use it in your project, you're incurring a massive maintenance burden. And if you want top performance, you might have to maintain multiple implementations across many architectures. And with assembly, there are no guarantees. All of the safety you get by writing regular Go, bounds checks, just simply aren't there. You can reference off the end of an array and assembly won't stop you. And channel your inner Donald Knuth. Remember the famous quote that premature optimization is the root of all evil. Make sure that this part of your code that you're considering optimizing actually really is a bottleneck. Make sure that you've profiled it, that you've benchmarked it, and it's really necessary to get this extra ounce of performance. But I'd like to, draw attention to this part of the quote that often isn't included. Yet we shouldn't pass up our opportunities in that critical 3%. That there are cases where this additional complexity really is justified. And what's in that 3%? Usually it means that you're either taking advantage of missed optimizations by the compiler or special hardware instructions. And this first case of missed optimizations is increasingly rare and usually isn't a great reason. Of course, there's always exceptions to the rule. But special hardware instructions really are a good reason to use assembly in certain cases. Uncommon cases are math compute kernels. There's a lot of assembly in the math package. System calls, so like low-level operating system interaction. There's a lot of assembly in the runtime for good reason. And something we'll focus on in this talk is cryptography. This is a case where, for the requirements for secure but performant networking, we really need fast cryptographic routines, and that usually requires assembly. So the purpose of this talk is not to say don't use assembly. It's to say if you're going to do it, then do it safely and make use of any tools you can, to make it safe. So we're going to start with a bit of a primer to Go assembly. I want this to be accessible to people who haven't programmed assembly before. I'm going to talk a bit about the problem as I see it and some of the challenges in this area. Talk about code generation as a potential solution. Then I'll introduce the Avvo library, which is a library I've written that I think can help. And we'll go through some examples. Vector.product we'll go through in a bit of detail. And then I'll finish up with SHA-1 as something that I think really demonstrates where this library can help. And then at the end, I'll just go through some future directions I think this kind of approach could go in. So let's start with a primer on how Go assembly works. And our hello world won't be hello world. We'll just do an add function. And I think anyone in this room would know how to add two numbers in Go. We'll just take two unsigned 64-bit integers and add them to return another 64-bit integer. If you're considering optimizing a Go function with assembly, then a good way to start is just to use the Go disassembler. And that will help show you the machine code that the compiler generated. So you can use the Go toolchain to build your code, and then go to objdump will show you what instructions it actually generated. And in this case, the output's something like this. And there's a load of junk in there, but on the right is what's really interesting. This is showing us the instructions that the compiler actually generated. And you can't use this directly, but the assembly you'd have to write yourself is very similar, so it's always a good place to start. If we want to provide an assembly definition, we have to start with a function stub. So this is just the same as a standard Go function definition, but it's missing the body. And when the build system sees this, it knows to expect to find an assembly implementation in another file. And the assembly implementation is going to be in a file called add_amd64.s. The AMD64 tells the build system to only build this on AMD64 platforms. And the assembly definition starts with this text line. So we've got the function name there. We've got some flags, this no split here, which we won't really go into in much detail. But something that's quite interesting are these numbers at the end. These are like really critical to explaining to the Go compiler how our function is structured. And in particular, we have to tell it how many bytes of arguments and return values we need. So the value is 24 here because we're writing a function that takes two 64-bit values as input and returns another 64-bit value, totaling 24 bytes. The 0 actually is telling the compiler that we don't need any additional stack space, but other functions you might need additional stack space for local variables. And then every function is going to start with some move instructions that are going to read the arguments as they're provided to us by Go. And all of the arguments in Go are passed to us on the stack. So what's happening here is we're reading the x argument from position 0 relative to the stack frame into the register AX, and then we're reading y into CX, and that's at position 8 relative to the stack frame. And then we actually issue our add instruction, and this is going to add what's in CX into AX. And we finish by writing the result, which is in AX, into return into the position 16 relative to the stack frame. And that's where Go expects to find the return value. And then we finish with the return instruction. So, at this point, you might be thinking, this looks fine. I don't see the problem. Looks really easy. I'll write all my Go functions in assembly. But it does get more complicated than this. And I'd like to, spend some time thinking about, what can go wrong? Or how does this get hard? And this number is quite evocative to me. This is the number of lines of x86 assembly in the standard library. And note that that really is just x86 or AMD64. So if we were to include Power and S390X and ARM, this number would be quite a bit higher. And let's drill down into the top-level packages where all this assembly lives. And note that right at the top here, we've got a heavy hitter, crypto, with over 8,000 lines. And crypto is in this awkward intersection where you need, top performance, but you also need complete correctness. Any error could lead to a security vulnerability. And we've got 8,000 lines of, sometimes really hard to understand assembly. Now, breaking it down even further by lines, by files. These are the top 10 files. And again, crypto is, a heavy hitter here, with some files coming in at 2,500 lines. And let's drill down even further. There's absolutely no expectation that you, digest and understand the code on this slide. I just want to give you a feel for what we're talking about. Maybe you can read in the comment. Let's just say that this spaghetti loop interleaves 2 quarter rounds, blah, blah, blah. Nothing with spaghetti loop in it instills me with confidence. And this is, this is all in the same file. This is the largest assembly file in the standard library. It really is write once code, in my opinion. If you were presented with this in a code review, where would you start, right? And actually, these two are different parts of the same file, but they're almost identical. So that's just a tour of the sorts of assembly that is in the standard library, and you might ask yourself, is this fine? And I'm not here to, start mass hysteria. I mean, this probably is fine, and the people who wrote this are actually world experts in cryptography and performance, and we're really lucky as the Go community to have these people working on this project. So I'm not, it's not a disaster, but maybe it's worth looking at. And here's actually some code from a few years ago in the standard library. Again, no expectation that you understand exactly what's happening here, but there is a bug in this. And around 2 years ago, I think Cloudflare discovered this bug. It triggers in rare cases, so it involves a carry, and it happens kind of 1 in 4 billion event. But Cloudflare operate at such a scale that they observed this. And the fix is just 5 lines from that snippet, and it fixes the carry condition correctly. And it was originally just believed to be a compatibility issue, that every now and then you'd have this rare event would happen and you'd disagree with the endpoint you were talking to and wouldn't work. But actually, it was later discovered to be a critical vulnerability, that this single rare event could be exploited to leak secret information. So it's for examples such as this that leave me wondering, is there anything else hidden in those 8,000 lines of assembly? And the Go project itself seems to have agreed. Around a year ago, they instituted the Go assembly policy, which lays out a number of rules for how assembly can be accepted in the standard library going forward. So the first is always to prefer Go, not assembly. And similarly, to minimize the use of assembly, that if we're going to use it, then it must be restricted to just the bottleneck that we're trying to optimize, and everything else should be in Go. That we should explain the root causes. That means it should be very well commented. It should have commit messages that explain why this is required, and in particular, if there are any future changes to the Go compiler that would render it unnecessary. There are actually examples in the last year of assembly code being removed from the standard library because of improvements in the compiler. And of course, we should always test it well, should fuzz it, compare it against reference implementations. But something I want to focus on is that the assembly should be easy to review. The guideline says, make your assembly easy to review, and ideally auto-generate it using a simpler Go program. And when I read this, I kind of took this as a mission statement. Code generation is a technique that has been used, for many, many years to manage this kind of complexity. And I'd like to just, make a statement that is kind of obvious, but it's worth reflecting on. That there's a reason people use compilers. They provide us with many, many useful features. You can structure your code using functions and if statements and loops. It will do all these useful things like instruction selection. It will do instruction scheduling. It will do register allocation. It will do a whole suite of optimization passes. And just because we're deciding to forego the compiler and write assembly ourselves doesn't mean that we want to throw all of these niceties out, right? Anyone who's written high-performance C has probably seen something like this, code littered with underscores and MMs everywhere. What you're looking at is intrinsics, and each of these functions is guaranteed to compile to a specific assembly instruction. So what you get here is that you're going to get the special instructions you want, but you're still writing C, so you still get register allocation, instruction scheduling, you still get all the structure that comes with C. Unfortunately, we can't do this in Go. There's also a concept of a high-level assembler, which is an assembly language plus high-level language features. And examples of these are the Microsoft Macro Assembler and NetWide Assembler. These have the concept of if statements and loops in them to add structure to your assembly. OpenSSL is obviously another package that has a lot of assembly in it. And they chose to use Perl, of all things, which is a pretty shocking combination of languages. So they have this thing they call Perl ASM, and almost all of the assembly in OpenSSL is this unholy mix. But there is a great package that has gained some popularity in recent years called PeachPy, and that's a high-level assembler implemented in Python. So you get to use all the niceties of a really high-level language in your code generation, but the end result is assembly. But I don't know about you. So PeachPy actually has some features to support Go specifically and has been used in Go projects. But I don't know, it makes me feel a little bit dirty whenever I'm using Python in my Go projects. So I thought to myself, what about Go? And I set out to provide a solution for this kind of problem for Go programmers. And hence the Avvo library was born. I even have a logo, so that's how you know it's legitimate. And a bit about the naming. Peach is based on peach pie, which was written in Georgia, and peaches being the state fruit of Georgia. I wrote this in California, and avocados are the state fruit of California. So naming things is hard. So the idea is that I want to provide a Go framework that presents an assembly-like DSL, so DSL being a domain-specific language. So the idea is that when you're using this package, it should feel very much like you're writing assembly, but actually you're writing a Go program. And some kind of non-goals. This is not a compiler. It's really supposed to be very close to the assembly itself. And it's also not an assembler. So what I mean by that is it doesn't actually output machine code itself. The result of using Avvo will be assembly, which will then be passed to the standard Go build system. And the programmer retains complete control, that anything that could be done in raw assembly can still be done with this package. But the goal is just to remove some of the tedium, some of the repetition that happens in Go assembly at the moment. So in terms of its features, an Avvo program is a Go program. You can use Go control structures in your assembly generation. What's happened? Yeah. Well, I don't know how to get that back. I can unplug it and try again. Is that okay for people? Well, I guess I'll continue for now. So the idea is that you can use Go control structures for assembly generation. That means you can structure your assembly using functions and loops and conditionals. But I think really one of the, if you like, killer features of Avvo is that it contains a register allocator. So you can write your functions using so-called virtual registers, and Avvo will assign the physical registers for you. So that means that you can assign these virtual registers to, what's going on? So what this means is that in your Go program, you can assign these virtual registers to variable names that mean something to you, so that when someone is reading your code and when you're writing it, it's much more natural. But then at code generation time, Avvo will actually assign the physical registers. Not just that, but in the example we had before, we had to deal with the complexities of loading arguments. We had to deal with the complexities of loading arguments from the stack as Go chooses to provide them to us. And this can actually get quite complex. So Avvo will handle the details of automatically computing these memory offsets for us. And this is kind of a small thing, but it will also auto-generate these stub files so that you can call your assembly functions from your Go package. So let's demonstrate these features by going back to the example we had before of an addition function, but doing it with Avvo. So first off, it's just a regular Go program. It's written in a main function. And then, but note that we start with an import that imports the Avvo framework. And we use this lesser spotted dot import, which actually brings all these symbols into our namespace. And that helps to create this kind of DSL-like appearance, where this code is Go, but it looks a bit like assembly. We declare the function with a text statement, but note that we don't have to provide any of these special numbers anymore. We can just give it a standard Go signature. And here, this is where we load the parameters into registers. Note that we use this param helper where we can reference the x parameter just by name rather than by a memory offset. And then we can use this GP64 helper, which will assign a virtual register to load that into. And we don't have to say that's going to be in register AX or CX. And then given these two virtual registers, X and Y, we can issue an add instruction on them. Note that Avvo actually contains one function for every single x86 instruction there is. And then we finish with a store into the first return value position. Finish with a return instruction. And then every Avvo program ends with a call to generate. So what's happening here is that all the previous instructions are building up an internal representation of the program. And then generate is going to process that. It's going to do liveness analysis and register allocation. And then it's going to finally print the output. So this is just a Go program. We produce the assembly by Go running it, and you'd probably put this in a Go generate line. We tell it where to put the assembly in the function stubs. And the result's going to look something like this, which is much like what we had before. Notice that Avvo has computed these numbers for us about how much space on the stack this function is going to require. Notice these memory offsets are also computed for us. And again, the registers are allocated for us. And finally, it auto-generated this stub file so that we can call it from Go. And just a couple of kind of contrived examples to drive some things home. Here's a mul5 function, which is going to multiply a number by 5 by adding it to itself 5 times. So we can just put the function in a loop. And when we run it, look, there's 4 of them. And this is a demonstration of loading a complex data type in Avvo. Completely made this thing up. So I've got a struct with a field called sub that's an array of complex values. What if I wanted to access the 5th position of this subfield? What memory offset would that be at? And in Avvo, what we can do is we can use this package statement to say, this function is going to belong in this package. What that means is that you can access any of the types that are defined in that package. And when you load that parameter, you can use this kind of chain syntax. You can say, I want the S argument to my function. I want the sub struct field. I want the 5th index. And I want the imaginary part of that, and I want to load that into a register. And then when I generate the code, it knows that that's at byte 52. So actually, if you look at Go assembly, you'll see that people almost deliberately pass in very primitive basic types because they don't want to have to work out these offsets. In Avvo, it's easy. So I'd like to just go through the library by going through a couple of examples. And what we're going to focus on is vector.product, which is a very, very common mathematical operation. And I picked it because, well, for one, it's real, but I think it's kind of complicated enough to demonstrate some of the features. So vector.product involves taking 2 slices or vectors of floats of the same length. And what you do is you take all the elements pairwise, multiply them together, and add them all up. And that's the dot product. So just to drive that home, here's our 2 slices of floats. What we're going to do is multiply them pairwise to produce this kind of intermediate array of products, and then sum them all up, and that's the dot product. It's quite simple to do in Go. We're just going to take 2 slices as inputs. We're going to initialize D, and that's just going to be 0 initially. We're going to loop over our slice, multiply the values, and add them into this accumulating value D, and finally return it. So just to set a baseline, this pure Go version runs at around 970 million array elements per second. We'll call that our 1x like baseline. So suppose we need this to be faster, and we're going to set about implementing this in assembly. It might look something like this. So again, we declare our function with the standard function signature. And here we're loading the parameters. So what's happening here is we're loading 2 pointers to the base addresses of each of those slices. Those are going to be in registers X and Y. And then we load the length of the first slice into another register. We'll call it N. Now we need to initialize some things. This is going to be D, the accumulator that we're summing into. And we use this common trick in assembly. We XOR it to itself to set it to 0. And we'll also need an index into the array, and we'll XOR that to itself to set it to 0. And this is our main loop where all the work happens. We start with a label. We didn't introduce this before, but this is a way of marking a position in the assembly so that it can be jumped to later. And that's how you construct a loop. We're going to compare the current index to the length of the array. If it's greater than or equal to, then we'll jump to our done label. And then this is where the work actually happens. We're going to allocate ourselves a temporary register for the product. Then we're going to load x into it from the x array. Then we're going to multiply that by the corresponding y element. And then we'll add that into our accumulator d. And we finish the loop by incrementing the index and jumping back up to the top. And then this is the end of the function. We've got our done label that we'll jump out of the loop from. And we store the accumulator d into the return value. And then, as always, we finish with return and generate. So how fast is this? Well, clock's in at around 976. We were at 970 before. So, let that be a lesson to you. Don't do anything in assembly that the Go compiler is going to do. We basically just that's pretty simple code. The Go compiler can do that on its own. Maybe we beat it by a fraction, but So how are we going to beat the Go compiler here? And we have a few tricks up our sleeve. All right, trick number 1. We're going to use something special called a fused multiply add. So what we're doing here is just a loop where we multiply and we add. That's it. It turns out there are special instructions that do that in 1. So that's going to be our first trick. Our second trick, we're going to use vectorized instructions. So there's this beautiful thing called vfmadd231ps, which does 8 single precision fused multiply adds at once. So we should probably use that. And I'd like just to take one moment to reflect on the absurdity of that instruction name. If you're into this kind of thing, you should follow this. You should follow this parody account on Twitter that has various fake instruction names. So anyway, we're going to use vfmadd231ps to do 8 of these at once. It's going to look like this. So now we're not processing 1 element at a time, we're processing 8 at a time. So we'll go through the array like this, and we'll have this accumulator value at the bottom that we're adding into, like so. So that's going to be our second trick. We're going to use these vector instructions. But the third trick is we're going to use loop unrolling and pipelining. So in order to saturate the performance of this processor, we're going to actually process multiple blocks of 8 at once and have them all in flight at the same time, and that will allow us to cover the latency of that instruction. So now, here's what it's going to look like. I don't know how well you can see it, but we're actually going to be processing multiple of these blocks of 8 all at once. So here's an illustration of doing what we would call an unroll factor of 2. So we're processing 16 at once and adding into 2 accumulators. And we iterate through the array in chunks of 16 like this. And then at the end, we have to finish up by adding these accumulators together and then reducing them to 1 value. That's kind of a detail. So how do we actually modify our program to do this in Avvo? And I guess at the high level, it looks very similar to before, but we're going to use these special 256-bit wide registers. We're going to use that absurd fuse multiply add instruction, and everything's going to have a loop around it that multiplies it by this unroll factor. But we're also going to move our code generation into its own function. And I think this is really actually quite important, that this function can take a parameter called unroll, which is what unroll factor are we going to use? And what this ends up being is what I would call like parameterized code generation. And I think it's quite a useful idea. So when we define our function, we're going to actually include the unroll factor in the function name, and we'll declare it much as before. And again, actually, the parameters are loaded exactly the same way. And in initialization, what's happening here is that we're allocating multiple accumulation registers, and it's in a loop because it depends on the unroll factor. And inside the loop, we're allocating one 256-bit wide register, and we're XORing it to set it to 0. This is what the top of our loop is going to look like. And again, it's kind of similar, not exactly the same, but we have to do a bit of math to figure out, how many items are we processing per iteration of the loop. And this comparison is a bit different. Instead of counting up, we're going to count down. And all this comparison is checking is, do we have a full block's worth of array positions to process? And if not, we'll jump to the tail. And now this is the real meat of the work. This is what the loop body looks like. Notice that, again, everything is in this loop over the unroll factor. And here what we're doing is we're allocating a bunch of temporary registers to hold the X values that we're going to load from memory. And this is a move instruction that's going to load from the X array. And finally, this is where the actual work happens. We issue the fuse multiply add instruction that's going to multiply the X that we just loaded to Y that's going to come from memory, and then we're going to add it into the accumulation register. So this is where all the real work happens inside the inner loop. And I'm not really going to focus on this, but I just want to include it for completeness, that we need what's called I would call a tail loop. There might be stuff left at the end that isn't a multiple of a full block, so we have to process that one by one. And then finally at the end, we have these multiple accumulation registers which we have to add into each other and then reduce all that to one float. But again, all the performance critical work is happening in that loop. And finally, so we wrote ourselves this dot function that is going to generate an implementation with a given unroll factor. What's quite nice now is our code generator can take a flag, which is, which unroll factors do you want to use? So what's happening here is I'm defining a flag that's a comma-separated list of unroll factors, and I'll generate one function for each. So now we can see for different unroll factors, what performance do we get? So if we unroll by a factor of 2, remember here we've got 3 tricks. We've got the FMA, we've got the vectorization, we've got the unrolling and pipelining. But we're getting 15 billion array positions per second at an unroll factor of 2. Unroll factor of 4, we're going up to nearly 26 billion per second. Unroll factor of 6 gets slightly worse. But what's nice here is that we can just experiment with that unroll factor and see what happens on your particular hardware. And by the way, just a caveat, this benchmark is particularly nicely chosen. The array size is quite small, so the whole thing fits in L1 cache. That's why these numbers are quite so absurd. But anyway, I hope this gives you an idea of how you can use Avvo to optimize something real. And the last example we're not going to go into in as much depth, but I think it really demonstrates how these techniques can help. We're going to show how you implement SHA-1 using Avvo. SHA-1 is a cryptographic hash function, and it has a lot of structure to it. It has 80 rounds, and the constants and bitwise functions vary throughout those rounds. And there's a message update rule, there's a state update rule. And you can use Avvo to generate a completely unrolled implementation of this function. And here's just some snippets from it. So we can use functions in Go to implement, if you like, subroutines as part of the generation. And this is a bitwise majority vote function. And it looks, you can kind of see, it looks a bit like how you'd implement it in Go itself. But actually it's taking registers as arguments and returning another register. And here's the implementation of XOR of 3 registers. Again, it takes registers as arguments and returns another register result. And we begin, again, using loops to structure the code generation. So we're going to load an initial hash from memory. And this second loop is initializing the registers that are used in the inner loop. And then this is what the actual main loop looks like. And again, you don't have to understand all of what's going on here, but if you've looked at the SHA-1 spec, what's nice about this is you're using variable names that you would recognize, and that you've got this loop over the 80 rounds, which is kind of naturally structured, and then you're using these variable names that make sense, and you can look at this and see that, yes, this is implementing SHA-1, rather than some massive unrolled list of assembly instructions. And again, we can use conditionals to make the code generation more natural. What's happening here is that in the first 16 rounds, we need to load the message from memory, whereas in later rounds, we need to actually execute instructions to derive it from previous message values. So I think that these kind of code snippets, you don't have to understand exactly what's going on, but I think they show how you can manage complexity using this technique. And ultimately, what you end up with is a really quite short, concise program that expands 116 Avvo lines into 1,500 assembly lines unrolled. So I hope that you can see how Avvo can be used to manage this kind of complexity. I just want to finish with where I think some of these ideas can go. So firstly, one of my goals is just to use Avvo in real projects. And I would really welcome anyone in the community, sitting here today who's interested in using it and contributing. And actually, there's already a number of examples using it. Thank you to Damian Greisky, who converted all of his existing PeachPy projects to Avvo. It was quite pleasing to steal some market share there. Thank you to Marko Kevak, who actually presented a project using Avvo at GopherCon Russia, and he used it to implement bitmap indices. Thanks to Julian Mayer as well from the 4 blockchain project, who used Avvo in an elliptic curve implementation. But beyond this, I think my intention right now is to use Avvo to actually tackle a lot of these large crypto implementations in standard library and actually show how they can be simplified with these techniques. Another natural direction for Avvo, I think, is more architecture support. At the moment, it's x86 only. And I no doubt made a number of assumptions in the design, which, if I was to introduce other architectures such as ARM, that would iron out those kinds of problems. I think another natural direction is to make Avvo an assembler itself. I don't have direct plans to do this now, but these kinds of techniques are actually used in JIT compilers. So I think that could be a natural direction at some point in the future. But this is actually one that I'm really excited about, and I would love to see happen. It's like Avvo-based libraries, not huge libraries, but for example, if you look at an implementation of an elliptic curve using assembly, what you'll actually see happen is lots of multi-precision arithmetic. So a really natural thing to implement would be multi-precision arithmetic helper library in Avvo. And then anybody who needs to use multi-precision arithmetic in their assembly could use those subroutines. So you might have something like Avvo math big as a helper package. You could also have crypto or hash helpers that would be used in other people's assembly libraries. And then finally, I don't know if anyone's heard of the FFTW project, the fastest Fourier transform in the West. So this is a really, really mature project, and I wouldn't expect to reproduce it, but we can learn a lot from it. What it actually does is it attempts to find the fastest possible implementation of a Fourier transform on your computer, and it really makes very few assumptions about the structure of your processor or anything. What it does is it has a library of many ways of implementing Fourier transforms, and then it just does, if you like, a parameter sweep over this space, benchmarks all of them, and picks the fastest one. And this, I think, is a really cool idea. And actually, in the dot product example before, we saw a very tiny example of it, where we had a code generator that takes a parameter, which was the unroll factor in that case, and then we just tried them all and picked the fastest one. So I think having a library such as this allows you to produce these parameterized code generators. And then you can do optimal code generation based on parameter sweeps. So this is just one of a number of directions I think this could go in, and I think it could be really cool. But that's it from me. I hope you learned something about assembly, and I hope that assembly isn't quite so scary for you now, and that if you consider using it in your Go projects, you'll try and use Avvo. Thank you very much.